Okay.
To make all
When you
these
want
things
that,
work,
change the
possible
base,
for me.
save me.
Okay, and can you see the slide numbers just so that I can refer to them explicitly, or no?
Yes, we are in the number one.
Yeah, okay, good. If we ever get lost, I'll just refer to the slide numbers.
Great.
Okay.
I don't see slide numbers. I don't see the slide numbers.
Oh, I mean like in the viewer, but if they're not on the slides. It's fine.
So, hello.
Hi.
Well, when you want, you can begin.
Okay, great. So, thanks very much for accommodating me. I'm extremely sorry that I can't be joining you guys there. Hopefully this will work well. And I can hear you, so if you have any questions, please do just speak up and interrupt me. So I'm going to be talking about trying to disentangle what Jaynes called the omelette of ontology and epistemology in quantum theory. And so the main focus of my talk is going to be a particular aspect of that omelette, which is the confusion between causation and correlation. So that's, correlation is a kind of I would say it's an epistemological concept, whereas causation is an ontological concept. And there's an analog of this omelette of, confusing distinction between correlation and causation in the classical sphere. So I would say a lot of recent progress in the field of machine learning, which is about trying to infer causal relations from observed correlations, has clarified that what held us back in the past typically was not having conceptual clarity on certain distinctions. So the first part of the talk is going to be about how to distinguish correlation and causation, and I'm going to apply some of the techniques from machine learning to talk about Bell-inequality violations and how to secure a causal explanation of Bell-inequality violations. And that's going to basically lead into how I think a research program that tries to separate influence from inference in quantum theory should look like. And then we'll see how much time we have left, but I could say a few words about formalism for inference in quantum theory, and then I probably will run out of time, but if there's any time left, I could talk about the underlying reality in quantum theory and how to describe causal influences. Okay, next slide, please. So to motivate the distinction between correlation and causation, I like to describe Simpson's paradox. So this is a paradox of statistics. The idea is that you have a large population of sick people, and for some subpopulation you administer a drug, and then you look at the fraction of that subpopulation that recovered, and you look at the fraction of the subpopulation who didn't get the drug who recovered. And what you notice is that recovery is correlated with taking the drug. So a naive interpretation of conditional probabilities as somehow representing causal influences would suggest that the drug is effective at recovery. But the surprising thing is that if you condition on gender as well, so you look at the subpopulation of men and the subpopulation of women, you find that the inequality goes the other way. So next slide, please. So that seems surprising. If you haven't seen this paradox before, I provided a little data table that gives a particular instantiation of this. And so the confusing thing is that it would seem that if you interpret these conditional probabilities in a causal way, it would seem that if you're a man or if you're a woman, then you shouldn't take the drug. But somehow, if you're a member of the general population, you should take the drug, and that doesn't make any sense. So I think that, although in the statistics textbooks they point out that there's no contradiction of classical probability theory here, to my mind, really understanding what's going on in this paradox means that you should understand whether or not you should take the drug. And to really understand that, you need to have a causal analysis of this situation. So, next slide, please. The one possible causal structure that could underlie this drug trial is the one I showed here. So the idea would be that the treatment variable, whether you got the drug or the placebo, can causally influence whether you recovered or not. And possibly also the patient's gender might influence the probability of recovering or not. And I think the reason it seems like a paradox is that this is intuitively what we think is going on. And if this is what's going on, then it turns out you can't get the inequalities that I showed you on the last slide. Because if this is what's going on, you can just take a weighted average of the probability of recovery given taking the drug for the men and for the women. And if it's a higher probability of recovery when you don't take the drug for the men and for the women, then by weighting those, it's not going to change that inequality. So you're going to expect a higher recovery for not taking the drug overall. So this can't explain what we saw. Next slide, please. If you imagine that the causal scenario is this one, where the gender also has a causal influence on the treatment variable, then you can explain it. So the idea is that this was not a properly randomized drug trial, and whether a given patient got the drug or not depended on their gender. So you can imagine that it was sort of up to the patient whether they got the treatment or not. And so this blocks the what I just described, because now you can't just weight on gender. You would have to weight each equation with the probability of gender given that they got the treatment. Those things are correlated now. But more intuitively, you can say, well, the reason we saw Simpson's paradox is because, for instance, men are more likely to recover from this disease than women are, regardless of whether they got the treatment. And men are more likely to get the treatment than women are. And in that context, if you say, I have a member of the population and I know that they're a man, I know that they got the drug, then you can reason, if they got the drug, they were probably a man, and if they were a man, they probably recovered. And so you can reason that there's a correlation between getting the drug and recovery, even if there isn't a direct causal influence from getting the drug and recovering. So the correlation can be a result of the common cause of gender rather than the direct cause of the effectiveness of the drug. Next slide, please. So the key thing, I believe, for getting out of the confusion of Simpson's paradox is to recognize the difference between two kinds of conditional probabilities. So the one on the right is, what's the probability of recovery given that you observe that somebody has taken the drug? And the one on the left is, what's the probability of recovery given that you make them take the drug? So the idea is that you, on the left, you intervene, and regardless of whether, whatever other influences might have determined whether they got the drug or a placebo, you replace that influence with, for example, a coin flip that's statistically independent of anything else that might causally influence recovery. And then if you see a correlation, you know that it's because the drug's effective. So in that way, you can, using randomized trials, you can determine whether something's correlation or causation. So more generally, I'd say that the distinction between correlation and causation is that correlation just says that if you learn about one variable, then you can come to update your knowledge about the other variable when they're correlated. But causation says that if you manipulate one variable, you can come to control the other variable. And so that is really a difference between mere inference and actual influence. Okay, next slide, please. So what I want to do now is talk a little bit about some modern work on inferring causal relations from purely observational correlation. So although randomized trials are a nice way of figuring out what the causal structure is, often you can't do a randomized trial. So in the case of determining whether smoking causes lung cancer, for example, you don't want to take would-be non-smokers and force them to smoke to establish that connection. And in the case of physics, like astrophysics, for example, you might have statistical correlations between astronomical variables that you cannot go out and control explicitly. And I would say in quantum theory, where you face limitations on how well you can control variables, for example, you can't control the position and the momentum arbitrarily well, therefore, you're going to have to rely more heavily on just the correlations to determine what the causal relations are. Okay, next slide, please. So I'm going to tell you something about the basic framework for causal inference. And so I'll call it causal model, basically a pair. One is a causal structure, and the other are some parameters. So on the left, the causal structure is just a directed acyclic graph. The nodes represent random variables, and the directed edges represent direct causal influences. So for example, you'll see that T has a direct causal influence on X in this example, and T also has an indirect causal influence on X via Y. So those are represented differently in this kind of model. And then in addition to specifying that, you specify some parameters. So one kind of parameter is just how variables that have causal parents, how they depend on their causal parents. So if I look at Y, for example, you'll see that it has W, R, and T as its causal parents, and so I need to specify the function that determines the value of Y from the values of its causal parents. And similarly for X, I need to specify how it depends on its causal parents. And then finally, for the variables that don't have any causal parents, the root variables, I need to specify the probability distribution over their values. Okay? And so I separated things out this way because the causal parameters are really about the influence that a certain set of variables has on another, whereas the statistical parameters can be thought of as features of our incomplete information about the variables. Okay, next slide, please. So it's convenient sometimes to eliminate some of these variables, so in particular the ones that are local noise variables, so they only influence one other variable. So for example, Q and R, Q was a local noise variable for X, R was a local noise variable for Y. So I can replace the deterministic dependence that X had on all of its causal parents with a probabilistic dependence on its remaining parents after I get rid of Q. So for example, I define probability of X given its other parents in terms of a parameter delta of the value of X as a function of all of its parents times the probability distribution over Q summed over the values of Q. So I can always do this.
Sorry, can you hear me?
Yes.
We had a problem with the sound. Can you repeat the slide? This is slide.
This is slide.
Starting with your last two equations, Rob.
Yes.
Okay. So the conditional probability of X given its remaining parents after you've excluded Q can just be determined by its deterministic dependence on all its parents. So that's the Kronecker delta between X and the function over all its parents. Multiplied by the probability distribution over Q. So that will just give me, for every value of X, what its probability is. So if I want to, I can always switch to these probabilistic causal models without any loss of generality. And that's what I'm going to do from this point onward. The next slide, please. Okay, so here I've just eliminated those local noise variables. Next slide. And now I want to say something about the kinds of principles that go into these causal models. So the first principle, I think the most important one, I'm going to call Reichenbach's principle. And it's the idea that statistical correlations must be explained causally. So if you see that two variables X and Y are statistically correlated, then it has to be the case that either X causes Y, or Y causes X, or there's some common cause for X and Y, or maybe there's both a common cause and a direct cause link between them. But it has to be one of those possibilities, that all correlations have some causal explanation. That's the idea. Next slide, please. So you might ask, well, how does Reichenbach's principle appear so far in this mathematical framework? Well, you'll notice that the root variables were assumed to be independently distributed. So if you look at W, S, and T in this causal structure, I assumed that they each had their own probability distribution. I didn't allow there to be correlation between W, S, and T. And so that's an instance of Reichenbach's principle. Because if I thought that W and S, for example, were correlated, then I would need to write down a causal structure that explained that correlation. So I'd have to put maybe a common cause between W and S or a direct cause between them. And so if I've committed myself to a causal structure that doesn't have those sorts of connections, then I'm committed to saying that they are independently distributed. Next slide, please. Okay, so now if you ask, well, how do I infer the joint distribution over all the variables from this causal model? Well, you can use that deterministic causal model I described you earlier to basically prove this equation I've written down, which is it's sufficient to just multiply for every variable the conditional probability for that variable given all its parents. When I take that product, I get the joint distribution over all the variables. Next slide. So these causal inference algorithms basically are trying to solve the inverse problem. The input to the algorithm is some joint distribution over a bunch of variables, and what the algorithm is trying to output is all the causal models that could have given rise to that joint distribution. And so I should mention this particular example I've been working with, I haven't got any, for instance, hidden common causes. So basically, I'm saying I worked on the joint distribution for all the variables, but sometimes your observed variables might be a subset of all the variables. And then you can still talk about causal inference, where you want to infer causal models that might include extra variables that are unobserved, but that can do justice to the correlations you've seen. Okay, next slide, please. So I'm going to tell you just a tiny little bit about how these algorithms work, so the state-of-the-art, well, some of the state-of-the-art in these algorithms, but mostly just the basic ideas and the principles behind them. So there's really two main tricks that get used. So next slide. The first trick is to look at statistical independences among variables. So at the bottom of this slide, I have a definition of A and B being conditionally independent given C. So the three equations below that are all equivalent ways of expressing conditional independence. So you can think of it as follows. So the first equation says, in the context of already knowing the variable C, learning B teaches you nothing about A. And the second one says, if you already know C, then learning A teaches you nothing about B. And the third one just says, if you know C, then your joint knowledge of A and B factorizes. So those are all logically equivalent by classical probability theory. And I'm going to denote that conditional independence in a way that's sort of conventional in this machine learning community as A perpendicular to B given C. So read that as statistical independence. Okay, next slide, please. So here's an example of how the causal structure influences the kinds of statistical dependencies you might see. So if I have a fork where B is a common cause of A and C, then generally A and C are correlated. So I denote that by not independent, so the perpendicular sign with a bar through it. So A and C are correlated, but if I condition on B, A and C become independent. So the idea is this, that the reason A and C are dependent is because if I learn about A, I can update my knowledge about C. Why? Because if I learn about A, I can update my knowledge about B, and updating my knowledge about B teaches me something new about C. So that's why they're correlated. But if I already know everything about B, then learning A doesn't teach me anything new about B. And so I'm not going to update my knowledge of C in that scenario. And that's why A is independent of C given B. Okay, next slide, please. Here's a couple of other examples. So a confounded cause, or confounded causal relation, is where B is a common cause of A and C, but there's also a direct cause influence from A to C. So again, you'll see that A and C are correlated, but now conditioning on B doesn't make them independent. They can still be correlated after conditioning on B. And the reason is that there's a new mechanism by which learning about A can update your knowledge of C, namely this direct cause connection between them. And then finally, the collider on the bottom is when A and C are both causes of B. So B is a common effect of A and C. So in that case, because A and C are root variables in the diagram, they're statistically independent. That's just Reichenbach's principle. But it turns out if I condition on B, I can make A and C dependent. And so that's a bit tricky to see, but if I think of an AND gate, for example, in logic, so if BE is just the AND of A and C, say they're all bits, and I find that B is 0, for instance, when I measure it, then if I learn that A is equal to 1, then I can immediately infer that C must be 0. So I have a correlation between A and C that's induced by learning B. So you can already see, sort of in these simple examples, that facts about the statistical independences on the right can teach you something about which possible causal model might have given rise to those independences. Next slide, please. Right, so this is my opportunity to test whether you've been following. So I'm going to give you a simple example where A, B, and C are the only relevant variables. They're only causally relevant variables. And suppose now that when you look at the joint distribution over A, B, and C, and you marginalize on the A-B distribution, you find it factorizes. So A and B are statistically independent. But if I condition on C, for example, then A and B are dependent. And furthermore, every other possible conditional independence relation does not hold. So for example, A is correlated with C, B is correlated with C, A is correlated with C if you condition on B, B is correlated with C if you condition on A, etc. So A independent of B is the only independence relation that holds. And so the question is, what's the causal structure that could give rise to that?
Collider?
I'm sorry?
Collider?
Yes, exactly. Next slide, please. Exactly, yeah, the collider, which is the last example we saw, ensures that A and B are independent because they're the root variables, but A and C, of course, are dependent, B and C are dependent, and A and B are dependent given C because of this effect that I described. So this is a great explanation of the correlations you've observed, but it turns out it's not the only one that's logically consistent with what you've observed. Next slide. So you could have something like this one, where C is now a common cause of A and B is also a direct cause of A. So in general, you wouldn't expect A and B to be independent in this kind of causal structure, but you can engineer things in such a way. So for example, suppose that C as a common cause makes A and B positively correlated, and the direct cause connection between them makes them negatively correlated, in just such a way that those two influences cancel one another and A and B become statistically independent. So that's possible. But it means that these parameters, like my probability of C and my probability of B given C, and A given B and C, those parameters have to be very carefully chosen to ensure that that cancellation occurs. And so if you look at the set of all possible parameters, there's only a set of measure 0 that achieves that. And so in the literature on causal inference, these kinds of explanations are considered bad explanations because they only hold if you fine-tune the parameters. Whereas the first explanation we showed, no matter what I choose for the parameters in that model, I always reproduce the independence relations that we see. Next slide, please. So that's the second principle. In addition to Reichenbach's principle, this no fine-tuning principle is the main ingredient that goes into these causal inference algorithms. So the idea, I'll just repeat it, is that a causal model of some observed distribution is said to be fine-tuned if the conditional independences in that distribution only hold for a set of measure 0 of the values of the parameters in that model. So for if you want it to be not fine-tuned, it should hold for all the values of the parameters in the model. Okay, next slide, please. So now I'm going to tell you about the second trick, which is to look not at the statistical independences, but at the strengths of the correlations in the model. Next slide. So here's a simple example. You have 3 binary variables, x, y, and z, and you observe that they're perfectly correlated. So with probability of half, they all take the value 0, and with probability of half, they all take the value 1. And now, if you look on the right, there's sort of 2 candidate causal models. And the one on the bottom, where there's a common cause of all three, is viable. It can explain what you've seen. But the one on the top, more surprisingly, can't. So let me just take you through that. So on the bottom, if lambda is also a binary variable, and it's independently distributed, it's uniformly distributed, so it's just a coin flip with probabilities of half for 0 and 1, and then x, y, and z are just copies of lambda, then I can achieve that joint distribution. But on top, I have x, y, and z now have common causes, but there's no triple wise common cause. There's only a common cause for every pair of the observed variables. And so it turns out that can't do justice to this distribution. And so I'll try to explain why. So first of all, look at the marginal on x and y for your distribution. It's also going to be perfectly correlated. So it's going to be probably half to both 0, probably half to both 1. And so I can explain that in this top causal model. If nu, for example, is a coin flip, and x and y are just copies of nu, then I'll make x and y perfectly correlated. But the problem is that if I allow y to depend on mu at all, I'll break the perfect correlation with x. And that's because x knows nothing about mu. X is not in the causal future of mu. And so if lambda depended non-trivially on mu in any way, lambda could not be perfectly correlated with x. So if I want the perfect correlation between x and y, then y has to be independent of mu, which means that y has to be independent of z. And by symmetry, I could also argue that x has to be independent of lambda, and therefore x has to be independent of z. So if I want x and y perfectly correlated, then they have to be independent of z in this particular causal model. So that's a kind of monogamy of correlations, which some of you might be familiar with from quantum theory. But here it's totally classical, and it just arises from facts about the causal structure. Okay, so what's nice about this trick for ruling out particular causal structures is that it doesn't even depend on this no fine-tuning assumption. There's just no way that this top causal structure can explain the correlations you observe, not even logically. It's just not possible. Okay, and people have, in our community, or the non-locality literature, have begun to think about these sorts of models, and I give some references here. Okay, next slide, please. So I've told you enough now to explain what these kinds of causal inference algorithms imply about correlations that violate Bell-inequality. So this is joint work with former master student, Chris Wood. Next slide, please. So here's your standard Bell setup. So in my notation, x and y are the setting variables for the two measurement devices. A and B are the outcome variables. They're all binary. And then, of course, you prepare some pair of particles and you send them off to the two devices. And so the first question you ask is, well, what kinds of joint distributions over A, B, x, and y are observed? Because those are going to be the inputs to the algorithm. Okay, so next slide. So it turns out that it's easiest for me to talk not about particular quantum correlations, but about these PR box correlations, which you may have heard of. So they're correlations that violate a Bell-inequality more than quantum correlations do. But it'll just make my life a little bit easier to use these simpler correlations, and everything I'm telling you would hold for quantum correlations as well. It would just make all the explanations a bit more complicated. So we'll look at these ones and see what happens in terms of what sorts of causal hypotheses could explain it. So the joint distribution over A, B, x, and y can always be specified by specifying the joint over x and y and the conditional of A, B given x, y. So the joint over x and y in this example is just, it factorizes. Each of x and y is uniformly distributed over its two possible values of 0 and 1. That's just by the setup of the experiment. And we assume that these things are being chosen independently and at random. And then what defines the PR box correlations is that the probability of A and B given x and y has the form at the bottom of the page. So if the product of x and y is 0, so that means if x and y have the values 0, 0, 0, 1, or 1, 0, then A and B are perfectly correlated. Whereas if the product of x and y has the value 1, which only occurs when x and y are both equal to 1, then A and B are anti-correlated. Okay, next slide. So the question is, what causal structure could give rise to this? And so I allow any possible set of arrows among these, including some unobserved variables that could act as common causes between them. Okay, next slide. So the most natural kind of causal explanation would be one where there's a common cause for A and B, which explains their correlations, but also the setting variables locally can causally influence the local outcomes. So if you even just look at the picture of the experiment, that's the causal explanation that suggests itself, that somehow the pair of particles together, were together at some point, so they act as a common cause, and then each particle transmits a causal influence that determines the outcomes at the two sides. Next slide, please. But the point of Bell's theorem is that this causal explanation is ruled out. And relative to these causal inference algorithms, it's just an application of that second trick. It basically says these correlations are too strong to be explained by this particular causal structure. So I'll take you through this in the language of causal inference. So how would I generate, for example, A and B perfectly correlated? Well, I could just make lambda a coin flip and make A and B copies of lambda. And if I wanted A and B to be perfectly anti-correlated, I could make A a copy of lambda and B an anti-copy of lambda, so just the flip of lambda. Now the problem is that whether A and B are correlated or anti-correlated depends on the values of both x and y, because it depends on the product of x and y. So for instance, if y is equal to 1, then whether B is correlated, is a copy of lambda or an anti-copy of lambda, will depend on whether x is 0 or x is 1. But B doesn't have any information about x, because B is not in the causal future of x. So there's no way for B to know whether to be a copy or an anti-copy. And therefore, there's no way to secure these kinds of correlations with this causal structure. Okay, so that's basically a way of proving Bell's theorem. And I should mention that Bell recognized this trick prior to the people in the machine learning community realizing it, but they rediscovered it in the 80s essentially, and then I guess figured out the connection with Bell's theorem. Okay, so this causal structure is ruled out, so the question is, well, what other causal structures might work? So next slide. You might think, well, okay, we need B to know something about x, or A to know something about y, so let's just put in a causal arrow from x to B. That'll solve the problem, that'll make it possible to generate these correlations. And that's true, this is a logically possible causal structure, it can explain these correlations. But, next slide, if I look at the statistical independences that these kinds of correlations imply, I find the following generating set of independences. So x is statistically independent of y, but also B is independent of x, and B is independent of x even given y. And A is independent of y even given x. So those two independences are what we normally call the no signaling conditions. So the distribution over B does not depend on the value of x, even if I know the value of y. And the distribution over A does not depend on the value of y, even if I know the value of x. So the question is, can this causal model on the right do justice to these independences without fine-tuning? Next slide. The answer is they can't, because in this causal structure, x has a causal arrow to B, and so for generic choices of the parameters in this model, you would expect B and x to be correlated. And so the fact that B is independent of x is something that needs to be enforced by fine-tuning the parameters of this model. So the idea is that whereas normally we might say, well, this causal structure is questionable because if I do the experiment at space-like separation, it would imply that there's a superluminal causal influence from x to B. My point here is that regardless of what you think about superluminal influences and whether they're plausible or not, what you can say is that by the lights of these machine learning algorithms, this causal explanation is a bad explanation because it requires fine-tuning. It basically says, if there's a causal influence from x to b, then you would expect some statistical dependence between x and b. And if you see no such dependence, as you do in quantum theory, it's just no signaling, then you have to explain that by fine-tuning. Okay, next slide. So we go to other possibilities. What if there was a common cause for X and B? So normally one would say, well, X was supposed to be chosen freely by the experimenter, therefore I shouldn't allow there to be something else which influences it and influences the distant outcome B. But again, even regardless of what you think about free will, the point is that this is still a bad causal explanation because it's fine-tuned. So next slide. The idea is that this common cause of X and B generically allows X and B to be correlated, and so if X and B are seen to be uncorrelated, then I need to fine-tune the parameters to enforce that. Next slide. So here's a more radical kind of way of trying to explain the Bell correlations. Suppose that there are retrocausal influences. So X causally influences lambda, which is in its past, and then lambda causally influences B. So some people have proposed this as a mechanism for explaining the Bell correlations. And the point here is, although the usual response is that somehow retrocausation is questionable, what I want to say is that this is, again, no different from the other explanations insofar as it also requires fine-tuning. So this retrocausal influence has set up a causal pathway from X to B via lambda. And so now generically there will be correlation between X and B. And if I want to make sure that they're uncorrelated, I need to fine-tune the parameters to do it. Okay, next slide. And next slide again. Okay, so the question now is, well, what remains? What out of all the possible causal structures that could underlie this could possibly do justice to these correlations? Next slide. And the answer is nothing. Nothing works, in the sense that either it simply is logically inconsistent with the observed correlations, that's what we saw for the Bell-type common cause structure, or it requires fine-tuning. And so in that paper with Chris Wood, we basically prove a theorem that demonstrates, here I'm just telling you, but we demonstrate that there is no causal structure that will satisfy the principles of causal inference for these sorts of correlation. Next slide, please. So here's the summary of the argument then. We've assumed Reichenbach's principle, we've assumed the no fine-tuning principle, and we've derived a contradiction with these particular kinds of observed correlations. That there's no causal explanation of them. But these were the PR box correlations. Of course, as I said, you do it with the quantum correlations as well. You get exactly the same statistical independences, and the argument goes through as before. Next slide. So this is the situation. You've got a contradiction with quantum theory and with experiment, and so the question is, what are you going to give up? So I would argue that it's very difficult to give up Reichenbach's principle, because I see that as central to most fields of science, to find causal explanations of statistical correlations. And I don't see any good reason that can be given for denying it just in the quantum sphere. Like, why should something that we adopt in the rest of science be given up just in the quantum sphere? And although the no fine-tuning principle, I think, is a little bit less secure than Reichenbach's principle, I can see ways, types of fine-tuning that are perhaps not so objectionable. Nonetheless, the spirit of that assumption, which is that these fine-tuned explanations are bad explanations, I think that's right. And again, across most fields of science, it's acknowledged that fine-tuned explanations should be rejected. And so again, I don't see a good reason for giving it up in the quantum sphere alone. So what you do when you don't want to give up any of the assumptions of your no-go theorem, you go looking for other implicit assumptions. So there are other implicit assumptions in this case. Next slide, please. Before we get to those implicit assumptions, let me contrast this type of proof of Bell's theorem with the usual set of assumptions, the usual way it's characterized. So typically, people will list the assumptions of Bell's theorems as realism, locality, which means no superluminal causal influences, something like no superdeterminism or the existence of free will, and no retrocausation is sometimes thrown in for good measure. And from those we derive the concentration. So let me just contrast that with what we've got here. So first of all, the realism assumption, I would say, was always a very controversial assumption in the sense that there's always been lots of debate about what it really embodies. Is it necessary? Many people have pointed out that it's hard to define a notion of realism that you could reject and still salvage locality, in the sense that most notions of locality presuppose certain notions of realism. And so if realism is supposed to be an independent assumption in this argument, it's unclear what it could possibly be. So this realism assumption in the version of the argument I've presented is replaced by Reichenbach's principle, which is the idea that correlation should be explained causally. And to my mind, that's you could think of that as a way of cashing out what the realism assumption really is doing. So it's basically saying that, yes, we need causation, not just raw correlation. I think it also represents accurately the view of some anti-realists. I think many anti-realists vis-a-vis Bell's theorem are basically saying they don't think that correlations need to be explained causally. And then the other three assumptions, the locality, no superdeterminism, no retrocausation, they all become special cases of the no fine-tuning principle. So they all fall under the umbrella of no fine-tuning. So the idea is that, as I showed you, if you assume no fine-tuning, together with the observed absence of superluminal signals, then you can derive that there should be no superluminal causal influences, because any such superluminal causal influences would require fine-tuning. And similarly, you can derive no superdeterminism, because that would, you can derive that there can't be common causes, and you can derive no retrocausation. So to my mind, each of these ways out of Bell's theorem, I think has been criticized at some point or another for seeming conspiratorial or implausible in some way. And I think the no fine-tuning principle is a way of formalizing that intuition that there's something conspiratorial about these explanations. Another nice thing is that it gets you away from locality in this discussion to just a more general principle about causal explanations, which means that the same sort of pattern can be recognized in proofs of contextuality, for example. Okay, next slide, please. So now I want to say something about what we're going to give up. And so next slide. The extra assumption, which I think is the one that we should consider giving up, is the fact that in the causal model framework, the unobserved nodes in the graph were assumed to be described by classical variables, even though they weren't being probed directly. And it was assumed all throughout that our incomplete knowledge of any variable was described by classical probability theory. Okay, so that was there from the very beginning. And so to my mind, this is the best place to try to understand it. It's best to give up this assumption in trying to understand the Bell correlation. Okay, next slide, please. So the idea is to replace these classical causal models with what I'll call quantum causal models. And
Rob, what slide are you on?
Yeah.
Are you on 45?
I'm on 45. It says quantum causal model at the top.
There we go.
So yeah, this is an attempt to innovate the formalism of causal models. So your causal structure is still a directed acyclic graph, but now the nodes don't represent random variables anymore. So they think of the nodes now as just labels for quantum systems. Some of these might be classical variables. That would be just a special case. And now instead of having functional dependencies of variables on their causal parents, you replace that with unitary connections between a variable and its causal parents. But of course, a unitary preserves the dimensionality. So the only unitary are actually from a set of variables to another set of, I shouldn't say variables, systems, quantum systems, from one set of quantum systems to another that preserves the dimension. So I might have to supplement this description with what I'm calling x bar, which is just some other systems that together with x have the same dimension as the composition of all of x's parents. So when I write u x bar given q s t w y, I just need a unitary from those variables q to y to x and x bar. And then similarly, there's a unitary that takes me from y's causal parents to y and y bar. And then there's this extra constraint of commutativity of the unitaries on their common causes. And then in addition, so those are like the causal parameters. They specify how things depend on other things. But there's also an analog of these statistical parameters, which are now not probability distributions over random variables, but quantum states. So density operators on the Hilbert spaces for each of these systems. Okay, next slide, please. So just as before, I can identify some of these local noise variables. I can eliminate them, essentially. And if I do that here, then I basically am defining completely positive trace-preserving maps from the parents of a variable to, I keep saying variable, from a set of quantum systems to the system that they influence. So for example, there's a map from S, T, W, and Y to X, which describes, sort of folds in the unitary and the quantum state on Q. So that's just the usual procedure in quantum theory. Next slide, please. But it's nice, instead of representing these things by maps, to represent them by operators. And so I just write that map as rho of x given S, T, W, Y. And so this is a special kind of operator that's meant to play the same role as a conditional probability in the quantum formalism. So I'm probably going to say a couple of words about that later. But the idea here is to just come up with a kind of quantum generalization of conditional probabilities. So this is like the indeterministic causal model, but in the quantum case. Okay, next slide. So here's the idea for trying to get a causal explanation of Bell correlation. So instead of adopting the sort of causal model you see on the left, where the unobserved node is a variable and all my knowledge is represented by probability distributions and conditional probabilities, instead I have the causal model on the right. So the only relation is that the lambda variable has been replaced by a quantum system, S, and all the probabilities and conditional probabilities have been replaced with these conditional quantum states and quantum states. And there's also a formula for how I should calculate the conditional of AB given XY. And in the particular case of AB, X, and Y being classical, that just reduces to a diagonal density operator that specifies a probability distribution. And what you can show is that doing it this way gets you exactly the usual quantum predictions. So in particular, you can generate correlations right up to the Simpson bound, which is the strongest quantum violations of the Bell-inequality. And so the basic idea here is that if we choose to innovate, roughly speaking, both the physics and the epistemology, right? So we're replacing random variables with something else, and we're replacing classical probability theory with this quantum theory of inference. Then, if we can succeed at that, we can say that we can be causally conservative. We can have the explanation of Bell correlations, which is the most natural one, namely just the common cause explanation. Next slide, please. Okay, and so if you're going to be successful at this, then you need a notion, a generalization of all the sort of standard notions that you would have in a theory of Bayesian inference. In particular, this notion of conditional independence. So on the left here, I've written down what you might expect the quantum analog of the notion of conditional independence to be in terms of these conditional states. And sometimes it is exactly this, other times it's a bit more complicated. But you get the idea that you have to define some notion of conditional independence. Next slide, please. And then once you have that, you can now talk about generalizations of Reichenbach's principle and the no fine-tuning principle. So the generalization of Reichenbach's principle would be, if I have two quantum systems now and they're dependent, meaning their quantum state doesn't factorize, then I have to explain that causally. They have to be, one has to be a direct cause of the other, or there has to be a common cause. And similarly, for the no fine-tuning principle, you now look at one of these quantum causal models, and if you want to explain some observed quantum state, you've only done that without fine-tuning if the quantum conditional independences are generic, so that it's fine-tuned if the quantum conditional impedances hold only for a set of measure 0 of the values of the parameter in the model. Okay, so next slide, please. This is the sense in which we can achieve a not fine-tuned explanation of Bell correlations that satisfies Reichenbach's principle. Because as I vary the choice of these conditional states and marginal states, it turns out I preserve all the conditional impedance relations in this graph on the right. Now, a question, is there a second set of equations at the bottom of this slide? Or no? Sorry, I'm just... Can you look at the next slide? Is the next slide also a quantum causal model?
Yeah.
Okay, let's okay. So look at the equation at the bottom of this slide. So what I want to say is that this is really just, I would say, a research program for getting a causal explanation of Bell's theorem. It's not complete, and I want to tell you a bit about what's missing here. And the idea is that in the classical causal models, these probabilities you added on, I think, should really be thought of as just using classical probability theory. So you're using a theory of inference together with a theory of causation to derive facts about statistical distributions. And so I think it's only fair to say that you really disentangled the omelette of causation and correlation in the quantum sphere if you can say that the stuff like the conditional density operators and the quantum states really is a theory of inference. And I think it's only valid to say that if it has all the features that a theory of inference would have. So it has to have conditionals, but those conditionals have to behave in a certain way. So for example, there should be a notion of Bayesian inversion, for instance. There should be a notion of how to propagate your beliefs from one system to another using conditionals. And there should be a notion of how inference interacts with the causal structure. So in the particular causal diagram here, not only should I be able to compute the correlations between A and B, I should be able to make the following sorts of inferences. If I learn A, I should be able to update my knowledge about S, and then based on that new knowledge of S, I should be allowed to update my knowledge about B. So that's what the equation at the bottom is meant to represent, that I should be able to write down, for instance, my new knowledge about B given A, and the background information about X and Y, in terms of a formula where I update my knowledge of B given S, and another one where I update my knowledge of S given A. For some reason my battery's about to die, which is strange because I'm plugged in. Hang on just a second. That's very strange. Done yet. It's trying to supplement these quantum causal models with something that could really be said to be a full theory of Bayesian inference. Next slide, please. Okay, so I'm wondering about time. I may or may not tell you about details of these theories. If you prefer, I could stop for questions. I could stop here and we can go to questions. I'm not sure how long I've been speaking for.
Yes, we are in time, so.
Stop for questions?
Questions.
Okay, in that case, why don't you fast forward to my correlation, my conclusions, which are further on slide 69. Okay, so let me just summarize. So I've argued that you can recast Bell's theorem with Reichenbach's principle playing the role that's usually played by realism, and you find that superluminal causation, superdeterminism, retrocausation all seem to be bad explanations of the correlation insofar as they require fine-tuning. But I think that quantum causal models are a promising avenue for actually achieving a causal explanation of the Bell-inequality violations. But it requires that one manages to take the quantum formalism and determine what in it is really about causal structure and what in it is really just about inference. And that's something we haven't quite succeeded in doing yet. And at the bottom of the page, I give you some of the references that this talk is based on. So thanks a lot.
What you think about reality, or something like that. I don't recall how you did it,
Sure. So let me put it this way: that the progress we've made thus far in disentangling inference from influence has taken a kind of top-down approach. So the work that Matt Leifer and I did basically asks. What sorts of features would you expect of a theory of inference, regardless of what it is inference about? So it's a bit like how in group theory, you talk about the intrinsic structure of a group without necessarily having a concrete representation in mind. Or in category theory, you do the same thing. So we've talked about, we've pointed out there's facts that conditional and Planck's relation should satisfy. So there's something called the semi-graphoid axioms. There's ways in which inference should play with the causal structure, that I should be able to, for example, make inferences step by step along the causal chain. So we have all these features of a theory of inference that we can characterize abstractly, and then we can argue that by defining quantum conditional states in a particular way, we can reproduce a lot of those features. So that's the question. If quantum states are meant to be states of incomplete information, and some part of quantum theory is all about updating your beliefs, what is that information about? What underlies the quantum states? What plays the role of the values of the variables in the classical theory of inference? And so that's the question, to my mind, of what's the reality of which the knowledge is knowledge about. So what I was going to say about that is just, I think there are good reasons to believe that, so first of all, I strongly believe that you need to answer that question. I'm not trying to avoid that question or say that it's acceptable to just have characterized quantum theory as a theory of inference without talking about what it's knowledge about. I think that's a very important question. But I think there's some good arguments to say that this whole idea of specifying the state of something, the physical state of something at a particular time, and then how it changes in time, there's reasons outside of quantum theory even for why we should reject that idea. And so this is the topic of my FQXI essay, where I basically say that if you grant that the only things that are physically significant are features of physical models that have some operational significance. So if I can vary features of a model without varying any of its operational predictions, I want to say, well, that's like a gauge degree of freedom. That's an unphysical part of the model. So you can argue that the division between kinematics and dynamics, like the specification of the set of possible states and the dynamical law for how they evolve, is conventional. It's gauged. It doesn't connect directly to what you can observe. So you can change the dynamics by compensating the kinematics. You can change the kinematics and just choose different dynamics and preserve the operational predictions. So there's an argument there that says that it's only somehow the union of kinematics and dynamics together that really is significant. And I think when you look at that carefully and say, well, what is this sort of unconventional distillate of kinematics and dynamics? I think it has something to do with causal structure. I think ultimately saying what causes what is what it boils down to. It's more relational. So, you know, in the quantum context, the unitaries that connect a set of systems to another set of systems, those seem to be real. They're not, in this approach, they're not about our subjective views of belief. And so somehow the idea is that we ought to think of the quantum states somehow as encoding our knowledge of those relations, those causal relations which are encoded in a set of unitaries.
It has a bit of the flavor, if I understand your answer. I don't understand your answer, but if I did understand your answer, it seems to have a bit of the flavor of David Berman's old slogan, correlation without correlata. You want to have causation without causata, or something like that?
Yeah, I used to say relations without relata. Yeah, but I guess you're right. I'm talking about causal relations without causal relata. Exactly.
I mean, particularly because you want to talk about causality in terms of density operators. You don't know how to identify density operators to state knowledge about some particular underlying reality, and you're resistant to introduce measurement, if I read you correctly. So you don't, whereas I'm perfectly happy to introduce measurement in that way.
Right.
You don't want to do that. Right?
Yeah, I don't want to pin the interpretation of the states of knowledge to some outcomes of experiment somewhere down the road. I want it to be knowledge of something to do with that electron, for instance. And so it's going to be, the causal relations that electron has with other things. And I'll just expand just a little bit on that, which is that if you think of a unitary, between one Hilbert space and another, so the claim here is that unitary describes reality, but I'm not saying that there's some place in the Hilbert space that the system is initially, and some direction in the Hilbert space that the system is finally. So that would be a psiontic kind of view, where I say, there's some definite quantum state, and then the unitary specify how that quantum state changes. I'm saying, the unitary specifies the relations between these two Hilbert spaces, and there is no sense in which the individual system is described by a physical state that corresponds to some direction in the Hilbert space.
Yeah, but it's a U-ontic view. U is
right.
And there's some similarity with Carl Cave's old view, to some extent. I mean, he didn't have any calculus, but he wanted to argue, or he argued vigorously that U should be considered objective, even though the state shouldn't. The state shouldn't be, for whatever that's worth.
So, Chris, how close is this to the stuff I talked about concerning locality? How close is this to the cubist view for how to secure locality in quantum theory?
Well, like I wrote you this morning, I don't understand it well enough to tell you. Rudiger thinks there's some distinctions, there's different diagrams going on, something like that. And I thought you understood that, but I certainly don't. I'm not in a position to say.
Well, it's just an area where there might be differences in the respective views on Reichenbach's principle and the requirement to explain correlations. So one of the things I was going to ask Chris over lunch was what, in fact, the cubist view on Reichenbach's principle was. But you definitely want it, but it's not obvious to me whether the cubists do or should want it.
Yeah.
Well, from what we saw, so I saw a talk by Rudiger Schacht recently on how to preserve locality, and he certainly had these directed acyclic graphs, which suggests to me that he at least endorses Reichenbach's principle. And yeah, it's just that there's sort of an analog of the schism between you, Chris, and the kind of view I'm endorsing here over in the machine learning context. So Davide has argued that one should not write down Pearl's causal diagram, but rather something he calls influence diagrams, where so he's basically motivated by an interpretation of probability theory in terms of decision theory. So he wants to pin everything to the outcomes of measurements this is not a quantum context, but he says, look, ultimately it's all in the service of decisions that agents are making, and those decisions that happen in the future. And so he has special nodes for the agent's interventions, and special nodes for the outcomes of their interventions, and it fits quite nicely with the cubist perspective. But to my mind, it loses a lot of what's appealing about these causal models. Like causal models allow you to make inferences about counterfactuals, which I think the decision theoretic approach doesn't.
Yeah, we might consider that a strength. A certain philosophical point of view might consider that a strength. Just to go backtrack a little bit, Rudiger has said outright that that he at least rejects the Reichenbach principle.
Oh, okay.
So I think what he finds of value, for instance, in the way you started to formulate everything, is that, for instance, your no fine-tuning principle, he would consider an extra normative requirement. So just as Dutch book says, you shouldn't gamble in such a way that you'll have a sure loss. You shouldn't make so when you draw causal graphs, you shouldn't do that in such a way that there's fine-tuning, I think. So he considers it a normative requirement. It's something that you add to the possible probabilities that you might write down. So there's that, and then where no signaling comes in, I'm sorry, I don't understand it well enough. Not no signaling, but locality, where it comes in, I don't understand it well enough yet. But there's certainly a lot of overlap, but as I understand him, the Reichenbach principle is rejected in our program, whereas it's not in yours. You want to generalize it in a certain way.
But if you want to conceive of it as a normative principle, why not endorse that normative principle and say...
Because it looks like it boils down to wanting a lambda somewhere. And you said it yourself just a minute ago. I'm euontic. There's your lambda. But, so you've taken the lambda off of the quantum system and you've put it onto causal relations, but you still want your lambda. And I think we still want to get rid of that lambda.
Well, if you look at the statement of the modified Reichenbach's principle, which I flashed up at some point, it didn't refer to any specific commitment to what the reality underlying our knowledge might be. It just said, if there are correlations, then there should be some causal explanation of them. So you could replace that with, if an agent wants to assign subjective degrees of belief that show, dependencies between systems, then that agent should also believe that there are certain kinds of causal relations underlying those systems. So I don't see how that would conflict with your...
I'll think on it, and eventually I will come back and say something. But I've got nothing to say right now.
Should we thank our speaker?
Yes.
Thank you very much. So, Peter, bye.
Thanks so much.
You can write
I think it's conference.
yeah, then you can write each other and
Yes. Yeah.
some things that you have to solve. Thank you
Okay.
for being here in this way. Bye.
Thank you. Bye now.